There's just nothing like a Formula One race. That scream of the engine, the blur of color, the sheer power. It's incredible. But what's really cool is that beyond all that thrill, F1 is basically a perfect, high-speed physics laboratory. So today, let's put on our imaginary lab coats and head to the track to see what it can teach us. All right, let me start you off with a question that honestly sounds a bit like a riddle. How is it possible for a Formula One car, one of the fastest machines on the planet, to be screaming around a track at 360 kilometers an hour, but at the end of a whole race, its average velocity is almost zero? I mean, that sounds completely impossible, right? Well, it turns out physics has a surprisingly simple answer. And I'm not kidding about the speeds we're talking about here. We're talking about a staggering 360 kilometers per hour. To put that in perspective, that is faster than a high-speed train. So just keep that number in your head as we start to pull this mystery apart. Okay, so to get to the bottom of this puzzle, we've got to start with the basics. And I mean the real basics. We need to talk about a concept we all think we know inside and out: speed. So, what is speed when a physicist talks about it? Well, it's what's known as a scalar quantity. Now, that sounds fancy, but all it really means is that it's just a number. It doesn't care about direction at all. It just tells you how much ground you've covered over a certain amount of time. That's it. Pure and simple.
Now, obviously, a race car isn't holding one single speed the whole time. It's speeding up, it's slowing down for corners, so that's why we usually talk about its average speed. Let's take an example, right? Say a circuit is 4 kilometers long. Over 72 laps, the car covers a total distance of 288 kilometers. If the whole race takes, say, 2 hours, you just do the math, and you get an average speed of 144 kilometers per hour.
And just to make sure we're all on the same page, speaking the universal language of science, SI units, that average speed works out to 40 meters per second. So we'll just use that number as our baseline going forward. Okay, but here's where it starts to get really interesting, because speed, that's only half the story. To really understand what's going on with that race car, we have to start talking about something else: direction. And that brings us to speed's slightly more complicated sibling, velocity. See, velocity is what we call a vector quantity. Again, sounds technical, but it just means it has two parts: a number, just like speed, and a direction. Velocity couldn't care less about the long, winding road you took. All it cares about is the straight line path from where you started to where you ended. And that path, that change in position, that's what we call displacement. Okay, if you take away one thing, let it be this: speed is like the odometer in your car. It just keeps adding up the total distance, only asking how fast. But velocity is more like a GPS. It asks how fast and in what direction. It only cares about that straight line from point A to point B. And believe it or not, this one little distinction is the absolute key to solving our entire paradox. All right, so we've got speed and we've got velocity. We're almost there. There's just one more piece of the puzzle we need, and this one is all about how you change your velocity. I mean, a car doesn't just magically appear at full speed, right? Of course not. It starts from a complete standstill on the grid, and then, boom, it's a blur in just a few seconds. Well, that whole process of changing its velocity, that has a name. And that name is acceleration. Now, here's something that might surprise you. In everyday life, we think acceleration just means speeding up. But in physics, acceleration is any change in velocity. And remember, velocity has both speed and direction. So, this is the key part. You are accelerating when you speed up, yes, but you're also accelerating when you slow down and when you turn a corner. Every single time a driver turns that steering wheel, they are accelerating. Yeah, it feels a little weird, but we really only think of acceleration as hitting the gas pedal. But in the world of physics, hitting the brakes, slowing down, or deceleration is just another type of acceleration. And why is that? It's simple. Because in both cases, your velocity is changing. And we can totally put a number on this. Let's say a car goes from 0, a standstill, to 20 meters per second. And it does that in 4 seconds. You just take that change in velocity and divide it by the time. The result? 5 meters per second squared. Now, that squared part can sound a little weird, I know, but all it really means is that the car's speed is increasing by 5 meters per second for every single second that passes. Of course, in the real world, it's rarely that smooth. If a car's velocity changes by the exact same amount every second, we call that uniform acceleration. But think about a real race. You've got gear shifts, tight corners, hills. A Formula One car is basically in a constant state of non-uniform acceleration. Its velocity is changing by different amounts from one moment to the next. Okay, we did it. We have all the tools we need: speed, velocity, and acceleration. So now let's head back to the finish line and finally solve that paradox we started with. So let's picture it. The race is over. The driver has somehow muscled that car through all 72 laps. It's an incredible feat of skill and endurance. And they have traveled a massive, massive distance. And where do they finish? They blast across that checkered finish line, which is, of course, the exact same line where they started the race. They are right back where they began. And that, right there, is the whole key. After driving 288 grueling kilometers, the car's final position is exactly the same as its starting position. And what does that mean? It means its total displacement, that straight line measurement from start to finish, is zero, nothing, nada.
And here is where it all just clicks into place. Remember how we said average velocity is calculated using displacement, not distance? Well, if the total displacement is zero, then the average velocity has to be zero. It's a mathematical certainty. It doesn't matter if the car hit 360 kilometers an hour on the straightaway. The final calculation only cares about the start and end points. So there it is. That's our answer. Despite having an average speed of 144 kilometers per hour and a mind-blowing top speed of 360, the car's average velocity over the whole race is, for all intents and purposes, zero. So it was never really a paradox, was it? Just a really cool piece of physics hiding in plain sight.
And these ideas aren't just for the racetrack. They are absolutely fundamental to how everything in our universe moves. So I'll leave you with a little thought to chew on. What other parts of your day, maybe a walk around the block or a ride on a roller coaster, are secretly being governed by these same simple but incredibly powerful rules of physics?